Hello, just waiting a few more minutes to see if more people show up. Okay. Probably a good time to get started. Looks like the class is yours for the moment, so if you have any questions, let me know. But as it is, this is the last week of our class. Apologies if I'm a little out of breath. I still am getting over COVID. Yeah. These are the topics I have for the rest of the class. I'm hoping I can get through all of them. As it is, I cut geometry a little short last week when I had to go running. But otherwise, I have shoehorned in a lot of the different topics that I'm hoping we can hit. And it should give a pretty decent overview of algebra in the next couple of days. So, yeah, without further ado, I'm just going to jump into it. Last time we finished off on rectangles. This time we're just going to start up on triangles. So triangles are three-sided shapes, as we know. There's a bunch of different kinds of triangles. It's not wildly important to memorize which type is which, but I did set up these slides to explain each type of triangle what we have. Understanding them can, like I have here, understanding them conceptually can come in handy. So equilateral triangle literally means all the sides are equal. So it has three equal sides, and because there's three equal sides, all the angles are also equal to each other. And since all the angles inside of a triangle add up to 180 degrees, then all of those angles for an equilateral are 60. It says there, imagine a triangle where all sides and angles are the same, like a perfectly balanced pyramid. We also have isosceles triangles. Those have two equal sides, and because of that, two equal angles, and then you usually have a third side that's a little bit different there. Like it says here, visualize a mountain that has two equal slopes on each side, but obviously the base of the mountain might not be the same. Also have a scalene. A scalene is just kind of its own thing. None of the sides or angles are equal to each other. And then a right triangle, you find yourself using the most in math classes. A right triangle has 190-degree angle. Is a right angle. The side opposite the right angle, so straight across, is called the hypotenuse. It says, think of a triangle with one corner forming a perfect square like the corner of a book. So those are just the types of triangles there are. Now, like with rectangles, we have to do the same perimeter and area with triangles. So the perimeter of any shape is just adding up all the length of its sides. Now with rectangles, we had the twice the length plus twice the width was the perimeter. But we don't necessarily have, well, I mean, some of the types of triangles will have equal sides, but not all of them. So an easier way of thinking about it is just add up all the sides. Like I have here, a written formula isn't necessary if I needed one. Oh yeah, you are. It'll build up. Some people are getting out of work at 6 o'clock instead of being able to show up here at 6 o'clock. Yeah, see, we're up at 2. But yeah, it tends to build up class-wise from 6 to 6:45. There's one reason I've always done a significant amount of review, but I'm not going to have enough time to do a ton of review this week, so yeah. But yeah, perimeter of a triangle, you just add up all the sides together. And then area of the triangle, that one does have a unique formula. That one's pretty useful, actually. So the area of a triangle is a measure of the region it occupies within its boundaries. So the formula to calculate it is typically given as half the product of the base and height. I usually write it as 1/2 BH, but 1/2 base times height is fine too. Yeah, okay. All right, guys, still a little out of it. So I'm just gonna write down the first one. So we have an equilateral triangle, and remember, equilateral means all the sides are equal. And it's telling us that we have a side of 10 centimeters. And we are looking for both the perimeter and the area. Okay. So remember, if all the sides are the same, you have kind of a perfect triangle. Pretend that's perfect. Every side is going to be the same. So if I had to figure out what the perimeter was, well, I'm just going to add up all the sides, right? 10 plus 10 plus 10, or 3 times 10. We end up with 30 centimeters, no matter how you want to look at it. And there we go. Now to find the area, we don't quite have enough information to find it at this point. I'll show you what it is I mean, because like I said, the area formula is 1/2 times the base times the height, but we don't know what the height is of this triangle, right? Let me actually figure that out real quick. So to be able to do this problem, we actually need to know what the measurement of this height is. So just for the sake of this problem, I'm going to go ahead and say, hey, the height is 5√3. Normally, you would have to find it yourself using something called a Pythagorean theorem. I do have that. In a couple of slides. But like any other problem, you take the formula and you plug in what you know. So you have the area, it's 1/2 the base. Now the base measurement is just the measurement of the base, the measurement of the bottom of this thing, which is a 10. And then you have to multiply by the height, which again, in this case, I'm just going to use as a given, 5√3. I could have used a decimal. Doesn't really matter. And then I would multiply everything together. 1/2 times 10 is 5. Times that thing, we end up with 25/3. And yeah, that's probably not going to be a great answer. So what I'm going to do is I'm actually going to go ahead and get a decimal for it now. This is 43.3013-ish. Now, since this one was centimeters multiplied onto a height in centimeters, centimeters times centimeters is centimeters squared. Does anybody have any questions on those? Nothing yet? Okay. Let's see. So the second one says we have an isosceles triangle and the equal sides measure 6 inches. Remember, isosceles is the one that has 2 of the same side, 2 equal sides. Base is 9 inches long. You know, I made all these problems and I neglected to realize how much I would be needing the Pythagorean theorem. So let's fix that. Let's go back and do the Pythagorean theorem for funsies. Call it good for these problems for now until we have a little bit more information. Unfortunately, unless all of my examples are right triangles, can't get away with not knowing the Pythagorean theorem yet in order to find the areas of these triangles. All right. So, real quick, we have this wonderful little theorem that relates all the sides of the right triangle together. Now, you might say, hey, you just said that we can't get away with what we're doing unless we had right triangles, but this only applies to right triangles. So how are we going to make this work? Well, if we go back to that figure I drew for the first problem, notice that in order to find the height, I had to make kind of a line straight through my triangle. Well, this made us have 2 right triangles right here. So what ends up happening is on all of these triangles that aren't right triangles, we're just going to make a straight vertical line to give the height, and we're going to work with that to make a right triangle. Now, in a right triangle, the square of the lengths of the hypotenuse, which is the side opposite the right angle, it's the long side, it's equal to the sum of the squares of the lengths of the other 2 sides, or you can call them legs. So that always ends up being a squared plus b squared equals c squared, where c is the length of the hypotenuse. A and b are the other 2 legs. So for instance, we have an example that gives us 2 legs, one's 3 units and one's 4 units. You can find the length of the hypotenuse by plugging those in. So you'd plug in the 3 and you plug in the 4. So you get 3 squared plus 4 squared is c squared. Translates to 9 plus 16 is c squared. So 25 is c squared. When you square root both sides, you end up with a 5. So then you find the length of the hypotenuse. Now, based on this, the idea is as long as you have 2 of the sides of a right triangle, you can always find the third. That is the general idea. So again, if I went back to that previous problem where I just said, oh, this is h, take my word for it. The idea there was that I split off these as having 2 right triangles, and I kind of worked with one of them where this stayed that 10 centimeters, because obviously we can't change it, but if I chop this perfectly in half, this would have ended up being 5 centimeters. Now, based on that, based on us having the hypotenuse and this leg, well, we have 2 of the 3 sides of a right triangle. So you can find that one. And that's exactly how I found this, is by plugging in 10 for the C and 5 for, I forget if it was A or B, it honestly doesn't matter. But once you do that, you can solve for that third missing side. Okay. So before I go back to, I don't know. I think I'm content just going straight back to these examples. Based on that, we can now figure out both the area and the perimeter for this problem. So we have an isosceles triangle, which means that 2 of the sides are the same. I'm going to go ahead and draw a quick diagram. This is going to be horribly not to scale because the equal sides are both 6 inches. And then the base was 9 inches. Horribly not to scale. But we need the perimeter in the area. Well, perimeter is easy. You add up all the sides. Let's see, that's 12 plus 9, so that's 21. And then our units are in inches, so 21 inches. Then we need the area. Now the area, again, is given us by the formula 1/2 the base times the height. But we don't know the height. So what we have to do, we have to make right triangles out of the middle of this guy. It's going to be slightly better to scale. So this side is still going to be 6 inches. But this, if I'm taking just this part of it, it's going to be half of that. It's going to be 4.5 inches. And we need to know what the height is. But now we have all the information we need in order to find that. So we're going to write out the Pythagorean theorem. Now, it doesn't matter which of these sides you consider A or B. It doesn't matter at all, because remember, If I have something squared plus something squared, it doesn't matter how I'm adding them. As long as they're being added together, we end up with the same thing. So it doesn't matter which leg is which, as long as you make sure that this hypotenuse is the one that goes over here. That's the important bit. So let's just say that A is the height. But we don't know it, so I'm just gonna swap that out for an H. Now the B would be the other leg, so that'd be 4.5. And the C squared, well, we know what C is, 6. Now this thing we need to solve for that H. So I know what that is, but I don't know what that is. We're gonna throw it at Mr. Calculator. 4.5 squared is 20.25. So we're gonna solve for that H squared, so we're gonna get rid of this guy first. So we have H squared is 15.75. And now I need to solve for H. Remember, if we have a square and we wanted to cancel that out, the opposite of a square would be a square root. So we do need to square root both sides. Now I show it, it looks awful, but it's, that's a square root. So the H is equal to, put square root of 15.75 in the calculator. I get something around 3.9686. Now, seems like a lot of work, but it's honestly not bad. Once you've done it a couple of times, it's really just plug stuff in and work it out until you have your variable above. Now, don't forget what we did that for. We just wanted the height. Now that we know the height, we can go back and figure out what our area is. So our area is 1/2 of the base. Now the base of this whole thing was 9 times the height. Well, we just figured that out. That's that long string of decimals. That can be as ugly as it wants to be. I don't really care as long as it's a number, right? All right. Well, let's throw it at the calculator, see what we end up with. Looks like we end up with 17.8587. Then we need our units. Everything was in inches, so inches times inches would be inches squared. I'll leave that one up there for a minute so you guys can stare at it and process a little bit. Do you have any questions on any of this? No questions, okay. Y'all just gonna let me talk my way through this whole class, huh? That's okay. So number 3 says a scalene triangle has side lengths of 7 meters, 9 meters, and 12 meters. Find its perimeter and area.
Hello.
Hey Ruben, how's it going?
So far, so good. And you?
I'm alive.
That's the most important, huh?
One could say so. I'm still getting over COVID from last week, but it's
Right.
it's fun. It's fun. I have like no immune system. It's great. So I don't know how if people started getting this at the beginning of things and it was worse than how I felt over the last week. I don't know how anybody made it because I sure as hell wouldn't have.
Exactly.
Easily the worst I've felt in my adult life, other than a 4-day kidney stone. That was fun. That was a lot of fun.
How are you feeling now?
I feel like I have a bad cold, which is far better than feeling like I have a bad flu, which was far better than feeling like I had COVID bad. So, you know what? I'm good with it. I will take it.
Okay, hope you get better and better.
Thank you, sir. You know what? This problem isn't going to work out as nicely as I'd like.
Exactly.
I'm going to change this to be an isosceles as well. I was trying to see if I can use artificial intelligence to write problems for this class is that it writes good problems, but a lot of times the problems require much more than what we're trying to cover. So having to play with that a little bit. Yeah. So I just changed this one to be an isosceles. So we have 9 meters on both of these side ones. And then 12 meters is the base. So we need our perimeter and our area. Our perimeter is adding all of the sides together. So 9 and 9 is 18 plus 12 is 30, and everything is in meters. So this will be in meters. Now the area gonna be tricky just like the last couple. Oops. I need to write BB. I don't have a pellet gun handy. H. So just like the last ones, we need to know what the height of this triangle is. We don't have enough information for that right now. So what we can do is we could take half of that triangle as a right triangle. And then use the Pythagorean theorem to figure out what the height is. The Pythagorean theorem, again, a squared plus b squared is equal to c squared. So it's the leg of the triangle squared plus the leg of the triangle squared is equal to the hypotenuse squared. So these guys are the legs, that one's the hypotenuse. Doesn't matter which leg is which, as long as we have them both in these spots and the hypotenuse in that spot. So I'm just going to say it's h squared plus 6 squared is equal to 9 squared. See that? So leg squared plus leg squared is hypotenuse squared. We're going to use this to solve for h. Practice 36 over. We have h squared equals whatever that is. That 45. Now I'm going to square root both sides, get the h alone. And like I did on the first problem, I could just get a simplified radical here. But as we figured out, it makes more sense to get a decimal. So that's what I'm going to do. I'm just going to figure out what the square root of 45 is as a decimal and call it good there. So I get h is 6.7082. So now if I need to find my area, it's going to be 1/2 the base, which is 12, times the height, which is that thing. I'll get all into a calculator and we get something around 40.2492. Then you need your units. This was meters times meters, meters squared. Okay. Do we have any questions on that one?
So why we have a squared and b squared?
So you joined a little bit late. I'll go jump back and show you because I'm fairly certain you're not the only one who missed a little bit. But since we have so much to cover this week, I opted to not do any review. And this is, if I reviewed, it would literally just be roughly the same things, just perimeter and area of rectangles. But this is the Pythagorean theorem. This is something that relates the three sides of a right triangle together. So as long as it's a right triangle, the A and the B are the lengths of the legs, and the C is the length of the hypotenuse.
Mm-hmm.
So once you essentially have to find like in our case, we needed to find the height of those triangles. We made a right triangle out of it, and we can use this formula to find that height. So that's where that came from.
Okay.
Now I do have some more examples for the Pythagorean theorem. These are going to be a little bit more towards just using the Pythagorean theorem, not quite as much what we just did with it, which was using it to find the height. That's a very good application of it, but having more applications is useful to have. So let's see here. So number one, says that a ladder leaning against a wall forms a right triangle. If the base of the ladder is 6 feet and the height is 8 feet, what is the length of the ladder? Okay. So basically, we have this, and we need to know the length of the ladder. You can kind of see here's a wall, here's the ground, and then we have like a ladder leaning up against that wall. So we need to know the length of that ladder. Well, the ladder is always is in the hypotenuse. The hypotenuse is always right across from the right angle and the right triangle. And yes, I know my triangle gets worse and worse here. But we would be using the exact same formula. And these guys would be the legs of our triangle. So we have 8 and 6 feet. And then we're going to use those to find how long that hypotenuse is. So we're going to plug those in. So 8 squared is 64. 6 squared is 36. We'll C squared. 64 and 36 add up quite nicely together to 100. And then you can square root both sides to get the C on its own. The square root of 100 is 10. So we get that the measure of C is 10. So it is 10 feet.
So in this case, you multiply 8 by times.
Up here?
Yep.
Since we have the square on it, which is an exponent, that's saying I have 8 multiplied by itself twice. So this is an 8 times 8, so we end up with 64. Whereas this is 6 times 6, so we end up with 36.
And C stays the same.
Yeah, because that's the part we don't know.
Oh, okay.
Yeah.
Okay. Okay. So the answer is 10 feet is the length of the ladder.
Exactly.
Oh.
And see, like every other formula in math, in any of these classes, if you have a formula where there's, in this case, there's 3 variables. If you know 2 of them, you can solve for that third.
Okay.
That's where this guy came from. Let's look at the next one. The next one says a rectangular field has dimensions of 9 meters by 12 meters. Now go ahead and draw that real quick. What is the diagonal distance from one corner to the opposite corner? So if we're trying to find the diagonal distance, that's from here to here. Go ahead and do a line across You could see this makes right triangles, right? We could also put that little box there. That box is to signify that this angle is a perfect right angle. It's a 90 degrees. Okay. So we need to know this, which since it's, the hypotenuse of a triangle, I'm going to go ahead and call it C. Just because, hey, we're kind of used to having a C there, right? And of course, we're going to use the Pythagorean theorem. A squared plus B squared is C squared. So we're going to plug in what we know, which are these two sides. And we're going to work it out to solve for that C. So 12 squared is 144. 9 squared is 81. Equal to C squared still. Add these guys together, we end up with 225 is equal to C squared. Which you probably don't recognize, but I do. Is when I square root both sides of this to find that C, to get that C alone, this actually ends up being a perfect square. This happens to be what happens when you square the number 15. So the square root of 225 is 15. So now that we know that, we know that this length would be 15, the unit would be meters. 15 meters. Like I said, I'm not a stickler for writing answers to word problems in complete sentences like some teachers I've had, but at the very least, if you're doing word problems, make sure you have the units on your answer. Somebody asked me how far something is away, and I said C equals 15. You're just a weirdo, right? I'm a weirdo, but not for that reason. Number 3. That says a flagpole casts a shadow that is 10 meters long. If the flagpole is perpendicular to the ground and the distance from the top of the flagpole to the end of the shadow is 8 meters, what is the height of the flagpole? That's an interesting one. Now, they might kind of confuse you by how the problem's written, but it's still just a flagpole casting a shadow. We know we're doing right triangles. So just think, okay, well, where's my right triangle going to be in this? Probably the ground is going to be the base of it. The flagpole is going to be the kind of taller of the two legs. And then it's not even talking about the distance from the top of the flagpole to the end of the shadow, which would be the hypotenuse right there. So go ahead and start drawing that out. So it tells us that the shadow is at 10 meters long, and the distance from the top of the flagpole to the end of the shadow is 8 meters. So we get something like that. Assuming this is the flagpole, from the top of it to the end of the shadow, we have 8 meters, and the shadow is 10 meters long. And we're looking for the height of the flagpole. Okay, well, that's not too bad, right? Now, unlike the other problems where they've given us both legs and we've had to find the hypotenuse, in this case, we have the hypotenuse and one of the legs, and we're having to find the other leg. Well, that's fine. Write out the formula every time until you have it down. A squared plus b squared is equal to c squared. Now these would be our legs. We'll have h squared plus 10 squared is equal to 8 squared. So now we have that, we're going to clean it up. So that's going to be plus 100, equals 64. Oh, this might break stuff. This might break stuff. I don't think this is possible. For these problems to work, the hypotenuse has to be the longest side. You could actually see that happen on all of these problems so far. We had 6 and 8 for our legs, so we ended up with 10. We had 12 and 9, so we ended up with 15. I mean, even these awkward little ones where we solved for the h earlier, we ended up with around 4, so it was still smaller. So this problem, while it sounds like a decent problem, is physically impossible. We can't have 8 meters here unless this is leaning over, right? It doesn't make sense. Now, if we tried to solve it, the problem is that we end up with a negative 36 here. So we can't have our height squared be a negative number. So that breaks this whole problem. Again, I'm trying the whole right problems with, you know, artificial intelligence, but sometimes it's not very intelligent. So I think a better way to do this problem would have been with those numbers reversed. Because then these would actually work out. Because this hypotenuse has to be the longest side. So let's see what happens after I make that little change. Now, the only real difference is that these guys are going to be in a different spot, right? So now the hypotenuse squared is 10 squared and the leg squared is 8 squared. So all that's really happened is these guys flipped around. But that's a significant enough change to the point where when I subtract that off, I no longer have a negative 36, I have a positive 36. And that's a big deal because, well, I don't have a negative height. So we square root both sides and we get h is 6. In this case, it would be meters, so 6 meters. Sorry about that. See, there's plenty of bugs to work out. I'm not really worried about the robots taking over yet. They can't give me an example of a real triangle. Does anyone have questions?
What do you mean?
What are we worried about? What do I mean about what?
The AI can't give you an example of a real triangle.
So the problem here is that based on this example, where it was telling us that from the top of the flagpole to the end of the shadow, it's saying it was 8 meters, and then the shadow was 10 meters. The problem is that triangle that is given as an example is physically impossible. Like, you literally cannot have a right triangle where the hypotenuse is shorter than one of the legs. So that was the problem there. Now, what I did to fix it was I just swapped those numbers around. So that way that the longest side is now the hypotenuse. But the problem was I had that GPT guy, I had it generate me some word problems. And it gave me something that was physically impossible. Cool. And I don't think I care about making you guys doing problems this week because we got a lot of ground to cover. And honestly, if I just stop talking for a little while, I'm probably not gonna start talking again for a little while. So, you know, so do we have any questions on the triangle stuff? Anything we need to see more of? Any curiosities?
To be honest with you, this is my first time I see this kind of stuff, and I'm not too smart.
I'm pretty sure you're not the only one thinking that exact thing with this.
Yeah, but let's keep moving to the next one.
Well, next stuff is going to be moving into circles.
Okay. Anyway, we have an idea now how we can solve this kind of problems.
Yeah. Let's see.
Because when I saw this on the test, I said, how this works? How we can figure out this stuff? But now I have an idea now, just practice and practice.
Yeah, it can be tricky. I will say if you need more practice, you know, the slides are usually in there, but I do have a couple more problems that I'm obviously not going to be covering. If you want to take a look at those. And it looks like they're solvable. All right. So circles, we love circles.
Okay, circles.
So a circle is a perfectly round shape in which all points on the edge are equidistant from the center. It is defined by its radius, which is the distance from the center to any point on that edge, and the diameter, which is twice the length of that radius. It's the distance across the circle. Circles are encountered in many real-world scenarios, such as wheels, coins, and plates. You too may have seen a plate in your life. Now, since we're jumping into circles, we also have to get used to pi. So I will say one particular class I tortured a little bit because I I had them calculate pi by hand with long division, which sounds horrible, but it's really not. As it says here, it's just a constant number that represents the ratio of a circle's circumference to its diameter. So if you know the circumference of a circle and the diameter of that circle, if you divide the two, you end up with pi. So it's an irrational number, meaning it cannot be expressed as a fraction or a finite decimal. Value of pi is approximately 3.14159, but it goes on infinitely without repeating decimals. Pi is widely used in various mathematical and scientific calculations involving circles, such as finding circumferences, areas, and volumes. The radius is the distance from the center of a circle to any point on its edge. It is half the length of the diameter. And the diameter is a straight line segment passing through the center of a circle, connecting 2 points on its edge. It's equal to twice the length of the radius. Weird how that works, right? So that's pretty much the vocab lesson for that stuff. And then we need to go ahead and be able to compute stuff with circles, right? So first we take a look at the circumference. So circumference is basically the measure of the perimeter of a circle. The circumference of a circle is the distance around its outer edge. It can be calculated using this formula. Circumference is 2 times pi times the radius. Or you can write it as c equals 2 pi r. So for example, find the circumference of a circular garden with a diameter of 10 meters. Half of that is the radius, 5 meters. Plug it in, and you get 2 times 3.14-ish times 5, get about 31.4 meters. And one thing I will say is that a lot of times they'll round pi to 3.14. That works. I prefer if you do the 3.14159. Makes your answer a little bit more accurate. Or even better, most calculators have a pi button. Hit the pi button. Pi button is your friend. And area. So the area of a circle can be calculated using this funky looking formula. So the area is pi multiplied by the radius squared. So pi r squared. For example, if you have a radius of 5 meters, you plug it in, 5 squared is 25. You multiply the 25 times the 3 and change for pi, and you end up with 78 point big ugly thing square meters. Okay. Let's do a bunch. The first one is telling us that has a radius of 5 centimeters, find the circumference. I think I'm going to go ahead and find the circumference and the area. Just so we can see how to work that a little bit more often, right? These ones are a little trickier because once you put pi in there, people's eyes tend to cross over. So we have two formulas, C equals 2 pi r, and A equals pi r squared. If you get these confused at all, remember if I'm squaring a distance, that gives me an area. In this case, we have no squaring a distance. We in fact just have numbers multiplied onto like a distance. So this one is kind of one-dimensional. This one would be two-dimensional. So you have circumference and area pretty decently mapped out. Now, the only thing we need to do is plug in this 5. Now, what I tend to recommend is remember, hey, this pi is just a number, but you can kind of treat it like a variable until you don't need to, right? Because this is 2 times pi, but it's also multiplied by a 5. Well, I can multiply the 2 and the 5 together right now. So I have 10 pi. And you could throw that at a calculator if you want to. I know that pi is 3.14159, but if I'm multiplying it by 10, then that would be our circumference. Now, the units was centimeters. This guy's also going to be centimeters. Now for the area, pi r squared. Now the r squared I can do real easy. But multiplying that by pi, not so much, right? So 25. Let's see, got a pi button. 25 pi. Hit enter. Thanks, calculator. Appreciate it. There we go. This one in particular has this button, which lets me bounce back and forth between exact and approximate. You can kind of see it going nuts here. So I'm going to go with this one. I'm just going to go ahead and round it at this point. So that's 78.5398. Unit wise, this was centimeters being squared. So that's our unit, centimeters squared. Now, does that make sense to everyone? Number 2 says the diameter is 12 meters. Calculate its area. So just remember that the diameter is always twice the radius. So if I have that the diameter is 12 meters, then my radius is going to be half of that, 6 meters. Now I would take this and plug it into my area formula. Area formula still being pi r squared. We'll have pi 6 squared We have 36 pi. I get 113 and change.
This is so frustrating.
Sorry.
I just did the post test, right?
Yeah.
And the part that I struggled on was the radius and the circumference and all this stuff and diameter.
Mm-hmm.
And the only thing I didn't do was the pi.
Brutal.
That was it.
And it makes sense, doesn't it?
Yeah, it makes complete sense. Like, wow.
Yeah, that's the painful part, is when it makes sense after the fact.
F word.
Word. Word. Hmm. Do a couple more. For 3, circular table has a circumference of 3.14 meters. Find its radius. Well, that's kind of funky, yeah? Well, if I know that my circumference formula is 2 pi r, and I know what my circumference is, I should be able to find the r pretty easily, right? Let's divide off the 2 pi. This is just going to be somewhere around 1/2. Funky looking thing, but that's fine. 0.4997 is equal to r. Now you might notice that, hey, 3.14 is what we round pi to. So why didn't I just cross those out? Well, the main reason I didn't is because this is only accurate to pi up to the hundredths place. If I haven't rounded this off at all, this is accurate forever to thousands and thousands of digits. So I don't want to cross something out that is rounded with something that isn't rounded. If I had, I would only be able to say I was accurate to this many digits, which would have rounded this guy up quite a bit, and I would have ended up with 1/2, which makes sense because there was a 2 down here. But I didn't, just because I wanted that extra bit of being precise. Now, this was in meters, so this is going to be in meters. So it's very, very nearly 1/2 meter. All right, class is half over. I don't want to nap. This is the most I've talked in a week. The longest I've been out of my house in a week. Very tired now. All right. The area of a circle is 154 square centimeters. Find its diameter. All right, that's doable. Kind of similar to the last one where we're going backwards. We're given our area, we need to find the diameter. How am I gonna find the diameter? I don't know, I'm probably gonna find the radius and then double it. So if area is pi r squared, and that is area, I'm going to set those equal to each other. 154 is pi r squared. Now this should be interesting because I'm gonna have to divide off the pi because I need to get that r squared alone in order to be able to solve for r. So I divide off pi. 154 divided by pi. Something like this, I do recommend to take as many digits as you can. I'm personally gonna go out to this point just because, well, if I went out to either of these, I'd have to round, and if I go out this far, I don't. So that's what I'd rather do. 49.0197 is equal to r squared. Now I need to solve for r, so I'm going to square root both sides. So we're going to have the square root 49.0197. I get 7.0014. Now that's our radius, but remember, we wanted the diameter. So I want 2 of that. The diameter is twice the radius, which is going to be 14.002814. This was originally in centimeters squared, so this is going to be in centimeters. Okay. How do we feel about this so far? Feeling good, we're feeling great, we're enjoying ourselves. Geometry stuff, not so bad. Okay. So I'm gonna need to take a quick break because, well, I feel busy. Still feel like crap. So I think we're gonna take about a 10-minute break before the rest of the class.
Okay.
Break until 7:30. So I'll put us on a quick break for that. And then we will continue on. We got fun stuff to do. We got one of the most fun things you're ever going to do in this class when we come back for this. I'm alive. I'm alive. All right. So I'm not gonna lie, I feel like crap still. So what's probably gonna happen is I'm gonna cover the next thing and probably get us out around 8, if that's okay with you guys. I blindly assume that everybody is saying yes.
I heard no complaints.
I also heard no complaints, but you will complain in a moment. Because I wasn't going to get to this particular part of math for a while. But we missed a few classes and I really wanted us to be able to cover it. So here is a crash course in higher math stuff. It's going to be fun. It's all going to be one formula, that one ugly formula. It's what we're going to do tonight. So it's dealing with quadratic functions. So I've always been bothered by where the phrase quadratic comes from, because quadratic is referring to a shape with 4 sides. Quad, get it? And you get that by squaring something. See, a square has 4 sides. So a quadratic function has a term that where the x value or whatever the variable is raised to the power of 2. So generally, they're in the form something x squared plus something x plus something. So it's kind of going down by, losing an x every time. If there's one thing I wish I could do, it's losing x's. Let's see. So ax squared plus bx plus c is the standard form of a quadratic function. The purpose of them is to model a wide range of real-world phenomena, such as the motion of projectiles, shape of parabolic dishes, trajectory of objects in free fall. Particularly useful when dealing with situations that involve variables squared or when analyzing the behavior of quantities that change at a nonlinear rate. So basically, we haven't gotten to actually working out things in straight lines and graphing straight lines. So we're just skipping graphing straight lines, jumping straight into what the hell is this? Now, for the most part, quadratic functions aren't bad. There's a lot of different ways of dealing with them, and they seem pretty complicated. But if you know the quadratic formula, you could pretty much throw any quadratic function at it and get the answers to be spit out, basically. And that's pretty much what I'm shooting for is, we're not going to have enough of a baseline knowledge to be able to develop quadratic functions or graph quadratic functions. But at the very least, if I had put this big ugly formula in front of you, you'd be able to take the A, B, and C and throw it at it, and it'll spit out an answer, and you'd be like, yep, that's it. Good enough. So the quadratic formula is a powerful tool used to find the solutions or roots, they're often called roots, of a quadratic equation. So by substituting A, B, and C from the formula into this thing, we can figure out what values of X make it correct. Now, an important thing to note is that since something has an X squared, the implication would be that it has at least two answers. It might be a little complicated to understand at the moment, but those two answers could potentially be the same number, or they could be opposite numbers. It could be wildly different. But if you look at this formula, there's a plus or minus in there. That's where the two answers come in. Because one answer is going to be negative b plus all that other stuff over 2a. And the other one is going to be negative b minus all that other stuff over 2a. Now, how you approach that depends on the problem. For the most part, when you're just doing algebra, it really just involves throw stuff at this formula, clean it up as much as you can, and when you have something that's not hideous with a plus or minus in it, you put a box around it and you call it good and you move on to the next one. If you're dealing with a word problem, you need to figure out both of those answers separately and figure out which one of them makes sense. And that'll make more sense as we actually work them out. But that's where that's coming from. So the next couple of slides, honestly, they're quite hideous looking, but it's just because there's not a good way to type this out. But the next couple of slides are just going to be an example. So in this case, a ball is thrown upwards at an initial velocity of 30 meters per second. Its height above the ground at any time t can be represented by the quadratic function. Here's the thing. Now, if you notice this h parentheses t thing right here, we haven't covered that yet, but this is something called function notation. This isn't saying it's h multiplied by t. This is saying that we have a formula that is called h, and the variable in that formula h is the letter t. So this is the height formula where t is the variable. So this is one thing right here. If you were to have to work something out in this, it would be reasonable to replace this piece with a y. Y equals thing. Function notation has its uses. We're not going to jump into them at the moment, but that's what that means. So big ugly thing basically just rolls with, here's a function that tells us the height at any given time in seconds. And it's saying, when does the ball hit the ground? Well, that could be kind of tricky, right? Now, conceptually, h of t equals, I don't really give a damn what this thing looks like. The general shape of this thing is kind of like that. That's the general shape. Now, we don't need to understand fully the graphs and where everything's going to be coming in to this thing. But if this is talking about height, and we have this thing going like that, where is this thing at the ground? Well, here and here, right? Well, whenever you use the quadratic formula, what you're doing is you're finding the intercepts on the x-axis. So when we find the answers, we're going to have two of them. One's going to be here and one's going to be here. But if I'm throwing something upwards and it hits the ground, well, I'm probably going to be looking for that one, right? Not so much this one, because that's where we started. So you'll see a little bit more of why these particular answers are going to be able to be weeded out in a moment here. So it says we need to find the time t when the height is equal to 0 because the ball hits the ground at that point. So you substitute h of t is 0. Not bad. Basically just take the whole thing and say equals 0. Bear with the next slide. They're hideous. It's all just little steps over and over and over again. So now you can use the quadratic formula to solve for t. Now, I'm just going to kind of gloss over everything that happens here. But the basic idea is that you have, this is a, that -5. This is b, 30. And this is c, 15. You take those pieces of information and you rewrite this with those pieces of information in it. All you have to do from that point is make it not ugly. And it's usually a couple of steps of clean it up as best we can. You can see that there's plenty of steps there. There's 1 step, there's 2 steps, 3 steps, 4 steps. Now, at the end of it, see, it started off with this big ugly thing where everything had been plugged in, and then it ended up with something a little bit neater, where it's like this thing is over a -10. Okay, no problem. I actually would have made that simpler, but whatever. Now what they do is they take the plus or minus and they split it. One of them has the plus, one of them has the minus. You get 2 possible values, 2 possible times when the ball is hitting the ground. Now, one of them, it tells us that we have to go with the one that's positive. One of them is probably going to be a negative number because, well, if I'm throwing it upwards from a height, it's already not at 0 anymore because it's in my hand. So it would make sense that the motion of this thing would imply that, hey, for it to have hit the ground before I'm holding it, it would have been in negative time. So that one doesn't count, and you have to work for the other one. Is apparently that answer. So nice, big, and ugly explanation. But again, the main things to keep in mind, you get a formula like this. There's your A, there's your B, there's your C. Take those pieces of information, write them out. Recommend writing them out. And then plug them into this formula. Work it out from there. Okay? Let's do a few. They're not the most fun, and there's also other ways to solve these problems, but we don't have enough time to actually get into factoring quadratic functions and all kinds of messed up stuff. So that's why I decided to roll with this particular method, because honestly, it's a catch-all. It'll give us the answer for everything. If you have 3 terms starting with an x squared, quadratic formula will give you your x equals. Now, the formula, I do recommend writing it out every time because it is useful to commit to memory. X is equal to -b plus or minus the square root of b squared minus 4ac. That whole thing is over 2a. And yes, I have done that so many times. I will never forget that. One day I will probably have Alzheimer's and I will forget my own name and I will remember this. This is like that cemented. Okay. Now, we need our coefficients. We need our numbers that we're going to be plugging into this. And it's all just whatever numbers are here. Now, I don't have anything here, so I'm going to call it a 1 because there's 1x squared there, right? This will be a -5. This will be a 6. All we have to do is take these 3 pieces, plug them into that thing. It's not the prettiest thing in the world, but it gets easier as you do it. Now, what I'm going to do is I'm going to go ahead and plug it in this first time with nothing but sets of parentheses. That way you can kind of see what's happening. Because as it is, I have a negative b. Well, my b is already negative. So when I do that, it's negative of my b plus or minus square root of b squared, my b is -5 squared, minus 4 times a, which is 1, times c, which is 6, all over 2 times a, which is again 1. Other than memorizing this thing and cleaning it up, we're effectively done. That's what the quadratic formula is going to give us. We just need to figure out what numbers this are, or this spits out. So negative of a negative, +5, plus or minus square root, -5 squared is +25. Minus 4 times 1 times 6, 4 times 6 is 24. All over 2 times 1. Oh, well, this is kind of nice, right? 25 minus 24, that's a square root of 1. So something interesting happens sometimes. Square root of 1 is just 1, right? So we get 5 plus or minus 1 over 2. Sometimes this works out very nicely and spits out a number. That doesn't happen all the time. It only happens if the problem we had originally was factorable, which means there was an easier way to do this. We just don't have time to learn it. So what you would end up doing is from this point, we're going to split this off as 2 separate problems. One is going to be this with the plus, and one is going to be this with the minus. That's it. 6 over 2, we get a 3. 4 over 2, we get a 2. And those are our answers, 3 and 2. Now, if that didn't clean up nicely, if this ended up being some obscure weird number and this wasn't a word problem asking me a distance or something, I probably would have just boxed it at the point where I have a square root and call it good. But that's how these guys are all worked out. Every single one of them. So again, wrote out our formula. I wrote out my A, B, and C to make sure I keep those straight. I took all of those and I plugged them into the formula with the parentheses to make sure that I don't make any sign errors. And then I just clean it up until I get an answer. So follow that structure every time and you will work it out fine. Okay. Who wants to see another one? Let's do another one. Number 2 says determine the values of x that satisfy the equation 2x squared plus 7x minus 3 equals 0. Okay. Same idea. A is 2, B is 7, C is -3. Again, I'm going to write the quadratic formula. X is -b plus or minus square root b squared minus 4ac all over 2a. I'm going to take that, I'm going to take this, and I'm going to put them together. X is equal to now negative b, so negative 7 plus or minus square root b squared, so 7 squared, minus 4 times a, which is 2, times c, which is negative 3, all over 2 of a, which is a 2. Now, if you can see it as you go, if you look at this 7 squared and you're like, oh, I could just write 49 there, go for it. If you see it as you go and you know it's simple enough, you can absolutely do it. Let's clean this up a little bit. This is 49. Now I have a negative multiplied by a negative in here, so I know whatever this is going to be a plus. 4 times 2 is 8, and 8 times 3 is 24. This whole thing is going to be over a 4. This is a 73. 49, 24. All right. Now 73, nothing really goes into 73, right?
1,
Okay, other than that,
a 0.
no, it doesn't.
A
You
0,
could have said
1,
73.
2, 3, 4.
Well, see, here's the thing. Nothing else is going to go into that. And depending on what it is you're doing this for, you might want to split it -7 plus root 73 over 4, -7 minus root 73 over 4, and get decimals. But we're not doing this for a word problem. We're just asked, hey, what is x? Well, this plus or minus is letting us represent this as two different numbers at the same time, right? So that's what we wanted. That's it. Oh my God. Second I'm feeling better, I'm gonna go down to whatever pharmacy feels like taking me, and it's gonna be like, yeah, whatever shots you got, just shoot me with them. Whatever's preventative, I don't care, I'll survive it. Just jab me with it, I don't care. Oh my God. Hope it sucks. All right. Oh no, that's an interesting one. Two numbered arrays. Find the roots of the equation. 3x squared plus 2x plus 1 equals 0. Yeah, same idea. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Over and over and over again. Now we're going to take these pieces and we're going to plug them in. X is equal to negative b, well, b is 2, so negative 2 plus or minus square root, let's cut corners where we can. B squared, b is 2, so this will be a 4. Minus 4 times a, which is a 3, times c, which is a 1. I don't really need to write that. All over 2a. Well, a is 3, so. Yeah. So we get negative 2 plus or minus square root of, this is 4 minus 12. So that's a negative 8 over a 6. Now, we are not yet at the point of playing around with what this means, having a square root instead of a radical. But hey, who cares? You know, you're going to see it eventually, right? So this is something called an imaginary number. And that is defined as the square root of a negative 1. Because what's squared is negative, nothing. Negative times a negative is a positive. Positive times a positive is a positive. I can't multiply the same thing by itself and end up with a negative. So it ends up being an imaginary number, which does have its applications on paper, actually. But that's what happens here. This gives rise to that our answer is going to be 2 complex numbers. That's what they're called. End up being called complex numbers when they have an I component to them. So what we're going to do is just take this at face value, and we're going to try to clean up that square root 8. So I'm going to show you what to do there. Now with that I thing, all that I'm really going to worry about is that. Now the square root of 8. 2 can come out. And then you can be a little bit cheap about this to clean it up a little bit. By just dividing both of them by 6 separately, and then they can reduce. I am aware that this one is probably a little too advanced for everyone, but this is roughly the type of problem you would see on quadratic functions. So this covers multiple concepts. This covers quadratic functions. This covers the quadratic formula. This covers imaginary numbers. This is called complex numbers.
Just give me an F. I'll take an F.
All right, here it is. You press it to pay respects. But yeah, so that ended up being a little more complicated than I would have liked it to be. But yeah, otherwise, if not for that negative, everything is exactly the same as the last couple. Hey, do we have any questions? Can I go to sleep now? I want to go to sleep now. I'm good. I'm good. I'm good. All right. So sorry, I don't have enough time to go crazy on imaginary numbers with you guys. I will say, I believe those are. The thing I wanted was right there. Believe. Actually, not 100% if those are in here somewhere. Imaginaries in here. Okay, I probably went a little too far.
Well, I'm
Actually-
pretty sure in your imagination it is in there.
I don't know if there are imaginary numbers on the ISET test, but this is the problem with making up problems with ChatGPT. I think I'm going to revise how I'm doing that. If that didn't work out as well.
Not in the slightest.
Yeah, so that particular problem, up until the imaginary number thing, complex numbers, you don't really need to know that stuff yet. I'm fairly certain those are not on the GED or HiSET. But that is where one of the applications of this formula go into. And you can tell that once you learn those, it's like 2 extra steps. That's the nice thing with math, is that when you learn something new, it's like, here's the crap you used to do, and now there's 2 more steps. We have successfully gotten past the building blocks on everything, and we have reached the, now things just get complex. Okay. So as it is, I'm gonna die. So I'm gonna call it good for the night. We're going to pick back up next time. Maybe a couple of quadratic formula examples just to round this off. And then reading and interpreting tables, circle graphs, not a whole lot of that. I want to get into lines. As much of the next class as I can is going to be graphing lines and doing formulas for lines. And then the class will be over. We have one more class after this. That is it. Go home.
Graphing lines. Do you mean like making those crazy 3D objects with nothing but straight lines?
That sounds awful. No, I mean like drawing a line with that. No 3D objects, just lines.
Yeah, it was in math class though.
Hmm?
Yeah, back when I was in high school, we learned lines, and we ended up drawing all this like line graph, and it ended up turning into this crazy 3D picture.
Are we talking something kind of like that?
No, it was more like a kind of like a I don't know.
Kind of like a cone, maybe?
No, it wasn't a cone. It started off as a cross, like Yeah, right there. It started off like right there with yeah, it started off with that, but we had to connect every line to the opposite number or whatever, and then it ended up being this crazy 3D picture.
Ends up kind of like almost like a cone on top of a cone. Sounds to me like you were doing conic sections. Yeah. Which we ain't even gonna look at, but that's the general idea, is that circles, ellipses, parabolas, and hyperbolas are all shapes that are made by a plane cutting through a cone. And yeah, it's a little unnecessary yet, but yeah, no, when it comes to next class, literally just straight lines, how to find them, how to make them, how to do them. Straight lines, that's all we're gonna have. Okay. Okay, y'all have a good night. I'm gonna go get some more rest, and hopefully the last time you guys see me for this class, I will not be disease ridden. Have a good night.